Okay, welcome back to our course in Cyber Physical Systems. We're going through Chapter 4, and today we're going to have a couple of slides of transitioning between the RFID topic that we covered last time and wireless sensor networks. And what we're going to discuss in this couple of slides is the network stack that can be equally used by RFID systems or wireless sensor network systems. So we have the TCP/IP stack, and that's I talked about that already, and we're going to talk a little bit more about it in this section. But I also wanted to introduce the OSI layer stack for networks. So the ISO, the International Organization for Standardization, has established a standard which promotes interoperability for software that is meant for network stacks. And that standard is the Open System Interconnection reference model that consists of 7 layers in the system stack. And at the bottom, you have the physical layer. So that's basically the specification that deals how do you connect to the communication medium. It could be air, it could be wired. So there is a standard for that applies to the connection to the physical medium. And then we progress up in the stack through the layers with higher levels of complexity until we get to the top layer, layer 7, which is the application layer, which is the one that deals with the actual application and the user interface. Now these layers communicate with the bottom layer and with the top layer. So the operation of the system traverses up and down through the layers, but any particular layer can interact directly with the peer layer of another device or another agent in the system, in the network. So as we have mentioned, standards are something that greatly promotes interoperability, ease of use, and reuse, and therefore lower cost. So we have two network stacks that we're going to be talking about. One is the OSI model, the 7-layer OSI model, and then we're going to show the specific stack up of TCP/IP, which actually doesn't have 7 layers. It has fewer layers, but we're going to discuss how the TCP/IP stack maps to the OSI reference standard. And the reason that TCP/IP have fewer layers and doesn't strictly conform to the standard model is that TCP/IP was created before the standard was deployed and actually specified. But there is a good mapping. There is a good mapping to some of the layers. In a sense, some of the fewer layers of TCP/IP inherit some functionality that are specified at some other layers in the OSI model. So these are the 7 layers of the OSI model. Bottoms, from the bottom up, again, the physical that deals with the connectivity to the physical medium. So for example, if we are talking about a network that uses Ethernet, so the actual Ethernet connection, the Manchester coding that is used, the serialization of the data that is used, how the collision mechanism that is using Ethernet, all that would be part of the physical interface because it deals how you connect with the cable, with the Ethernet cable. And then you start going up. Once that data gets serialized or deserialized, if you are having an incoming packet, how that data gets packetized and presented to the upper layer. In this case, the data link layer converts the raw data from the physical medium to the actual data structure that is going to be given to the network layer in this case. So it would, Ethernet is serial, so it would packetize it in bytes and then present that to the network layer. Now the network layer actually will build the network packets and is in charge of routing those packets. And this, it goes up from there to the transport layer, which deals with the actual end-to-end delivery of the packets to the network. So it would actually put the headers and some other quality of service type indicators. Then you have the session layer. So that would deal with authentication and authorization. So if you have any type of passwords and security, that layer would deal with that. So that the software in that layer deals with that. Then you have the presentation layer that would solve any data problems and deal with data compression. So if you were getting, for example, packets of MPEG video, it would be the software in the presentation layer in charge of decompressing the MPEG video and presenting it to the application. And then the application is the one, for example, if you are on a smart TV and you are streaming that video, the application layer would present that to the screen, convert that uncompressed video to the screen and also to the audio channel. So each layer has certain responsibility in the stack from a software perspective, from a system perspective. So that is the Osi Protocol Stack, the reference model. Now, not all implementations have to adhere to all the layers. You can have layers that are basically non-existent in the sense that if you don't have, for example, any authentication or authorization, then you really don't have anything in the session layer. You have a voice session layer, and that software is just passing from the transport to the presentation and to the presentation to the transport. There is nothing really there. But it has to go through the layer nonetheless to conform with the protocol standard, with the OSI 7-layer protocol standard. In contrast, the specific TCP/IP protocol has all the functionality of the OSI protocol, but it has fewer layers. And also it doesn't have a specific physical architecture because the interface of the link layer is what is called an MII interface or media independent interface, which abstracts all the data from whatever type of communication medium, whether it is wireless or wired or any other type. It abstracts all the software from the specific connectivity to the communication medium, whether it's wireless, wired, optical, it doesn't matter. Because there is a standard, what you call an MII, a media independent interface, independent of the connectivity and transmission and reception medium, that has been defined, and that is the bottom of the link layer. There is also a version of the MII which is called ADMII or reduced MII, reduced media independent interface, that uses fewer lines. So that's to economize on the connectivity, on boards, and things like that. So, but once you are in that link layer for TCP/IP, you have the link layer that serves the operating system device driver interface to the actual physical layer through the MII or RMII. So the driver in the data link layer is the one that talks and manages that interface. Then you do have a network. You do have a network layer that still does packet routing, and you have a transport layer, which is the one that in TCP/IP handles the flow of data between the systems. It also provides certain level of connectivity to the network for some applications through the sockets and datagrams. So you can have applications that all they use is the transport layer services for TCP/IP, doesn't go all the way up to the application. And this is a simple interface where you can open a socket and send packets to another socket on the network, to its IP address, and don't have to worry about any more elaborate application software. So that is available for TCP/IP. And then finally you have the application on top of that, which serves everything else. It does the it does what the presentation layer would have done in terms of authentication, data compression. It handles problems for the data. So all that is done in the application for TCP/IP. So the mapping is pretty good. You do have all the functionality, but you just have fewer layers in the stack, given the fact that it was conceived before the OSI model. So in a sense, the OSI model is a better model. It's more elegant and therefore more robust, although TCP/IP does have a very entrenched user base. It's everywhere, basically. Okay, so that gives you some background on the network stack that is going to support our discussion of wireless sensor networks. So what are wireless sensor networks? Basically, we're talking about a vast, spatially distributed number of sensors where each sensor can be a smart agent on the network. So these sensors are going to be doing data acquisition, are going to be doing monitoring of its environment, data monitoring, and also data processing at a certain level, but also data transmission and data procurement so that we can connect to analytic databases and tools. And they have applications in a wide range of areas that we have seen in the context of cyber-physical systems. So they have application in health, home, industry, military. So all the domains that we have seen already: security, automation, transportation. And we're going to see a chart towards the end of this chapter of how the main areas of wireless sensor networks map to the different domains that we have been discussing, with some examples that have already been tried and deployed in real systems. So what we have to recognize is that these sensors, they can have a structured topology or they can have an ad hoc topology, and we'll talk about what that means later on. And they also have some limitations on power. By design, they have limitation on power. We want them to be low power so they can be deployed, and they can be deployed without changing the battery often. And because of that, one way to have low power dissipation is to have limited computational capabilities. In a sense, not having a high clock rate or not having a large memory. So these are ways to minimize power from a design perspective. So by design, they are limited in power and in capabilities, but the great thing about it is that they are connected. So you can harness that connectivity and that symbiosis of the sensor being on the network with a lot of other sensors to distribute the processing and also to provide data for databases and analytics. So let's talk about the network topology problem when it comes to wireless sensor networks. So there are two cases. One is a structured network topology. So that's good because you know the topology, so you can optimize the software that deals with the routing and the traffic to deal with that specific topology and improve QoS, which is the quality of service, and also the throughput, which is the quantity of service. So we have quantity of service, that's how much data we can move through the network, and then we have quality of service, mainly meaning if we're moving the data at a certain rate, how many packets get dropped, how many packets get corrupted. So that's quantity and quality. We want both. But those are the main two metrics for network traffic. Quantity of service, throughput, and quality of service. So some of the specific metrics are here, like bit error rates, how expensive it is to do a transmission in terms of the bandwidth on the network, what type of latency do we incur from a message from the time that it gets sent to the time that it gets received. So message delay and any type of timing constraints that we can put on the messages. Another one is power. So how much power do we have to spend to send a specific message on the network? That's another metric for quality of service, and also packet loss. Packets that don't arrive at the destination. Differentiating from bit error rates. Bit error rates are raw bit errors that can happen on the data payload, as well, of course, as in the headers that result in packet loss. But packet loss is a subset of that, which is that you only have that corruption in the header and you never get the packet, you don't know where it needs to go, therefore you never can assess the quality of the data payload. So that's about network topology. We can have a structured, and we'll look at some topologies next. The other side is that we can have unstructured. We can have what is called ad hoc networks. So if we have a structure, we know what we're dealing with, and we can optimize, but clearly, since we already have a given topology, there is a lack of flexibility. There is a lack of flexibility. On the other hand, if we allow for ad hoc network topologies, essentially networks to self-configure on the fly to deal better and more intelligently with the environment and the situation, we have to make the software smarter, but we have a lot of flexibility. So in a sense, it's more expensive from a complexity perspective to deal with an ad hoc network, but it really gives us a lot of flexibility, and it really goes well with these wireless sensor networks, which the end application of them can vary a lot. So what you see is that in wireless sensor networks, ad hoc connectivity is not only a plus, but almost a must. And there are standards such as Zigbee and Bluetooth that they have certain ability to form ad hoc networks as part of their specification. So here are some network topologies, some well-known network topologies. The 6 of them. The star, so the star is when every network or sub-network entity, so each of these computers here, they could be a network themselves from a block diagram perspective. So we have the star in which all the entities, all the nodes in the network connect to a central hub, so every message has to go through this central entity. And the good thing is that if you lose one entity, the network remains intact as far as all the other nodes are concerned. Okay? The other extreme is the ring network. Very simple in connectivity, but all the traffic goes in a single direction through the ring, and it's very simple. So the networked entity, all it has to do is decipher, is this message for me or not? If it's for me, I act on it. If not, I pass it to the next entity on the network. That's all. So it's very simple. Now, the bad thing is that if one network entity goes down, then the whole network gets interrupted because you have that ring of traffic. Then you have the bus topology. That's where every network entity connects to the same medium. So Ethernet is a bus architecture for the network. So all the appliances that are on a specific Ethernet cable or drop, they are all connecting to the network. So in that sense, you have the robustness of if one entity goes down, the network is still intact. Notice that the difference between bus and a star is that here you have an actual appliance that is connecting the different nodes. In here, we're talking about the same wire, the same connection, the same physical media. And the advantage of this is that you don't have to have this central resource that has to deal with the traffic as you have in the star topology. You don't have to spend on that extra appliance. The drawback is that you have to deal with things like collision because there is no synchronization of all these different entities on the bus. They're all just going to transmit. So you have to figure out ways to smartly deal with that. For example, at the physical layer of Ethernet, the Ethernet physical access chips, what they do is they transmit. And electrically, the network is designed so that you can transmit and then listen. And then you listen, and if what you listen is what you send, then you know there is no collision. But if what you listen is garbled or is something that is not what you transmitted, i.e. is corrupted, then you assume that there was a collision. So you back up and wait. And you wait a random amount of time. You randomize the amount of time that you wait until you retry. And do it in this fashion, depending on the number of entities on the bus, you can eventually get a clear transmission. So that's what's happening actually on the Ethernet bus. Then you have the tree topology. And again, it simplifies the connectivity in the sense that each entity connects to 4. So it connects to a peer, the one that is at the top of the tree, and 2 at the bottom of the tree. So in that sense, it simplifies the connectivity. It doesn't require a central resource, but it does suffer from the drawback that if, depending on where it is on the tree, if one node goes down, you can lose part of the network. You can lose access to part of the network. For example, if this one goes down, then you lose access to this too. And remember that each of these icons, these computers here, they can represent an actual computer, server, appliance, or a sub-network itself through a hub. Then you have the fully connected, and this one is one where every entity on the network is going to have connectivity to every other entity on the network. So from a connectivity perspective, very robust because you connect to everything, but it's very expensive. And as the number of nodes in the network grows, the number of connections grows exponentially. So it really, past a handful of nodes, it really becomes not economically feasible to have that much connectivity on a complex network. And finally, we have the mesh topology, which is one where a network entity only connects to adjacent neighbors in what is called Manhattan directions, so horizontal or vertical. So this one is very nice and is used a lot in wireless sensor networks because it's not as complex as the fully connected topology. It gives the connecting entities a lot of access, and if you lose one entity, you can still get from one point to another, even if you lose one entity, even if it's not the most efficient route, but eventually you can get the message across. The other thing is that in the mesh, the connections wrap around, so it's not depicted here, but basically this one also connects to the one in the bottom, and this one, or this one for that matter, also connects to the one at the end. So you have this additional path that if you lose any one of these entities, there is still a path to go from any of the other ones to any other node. So these are 6 well-known network topologies. And this is just what I just talked about. But as I said, the real trend is for wireless sensor networks to adhere to an ad hoc self-organization, which calls for smarter sensors. But remember that we want them low power, so we want to make them simple. So there is a great need for simple yet smart algorithms for the deployment of sensor networks and the self-organization of ad hoc networks for them. Beyond the network topology, the networks can also be further classified in these groups. We can have global area networks. So those are networks that include often satellites to deal with transcontinental type communications. We have local area networks, so that would be, for example, a network at your home, a school, a building. Then we have metropolitan area networks, which are mostly referred to networks in a city or a metropolitan area. And then we have the wide area networks that refer to networks, for example, bound by a country or by a large area. And usually the communication or the backbone of those communication, because of the wide area, is optical or fiber optics. So if you look at the wireless sensor networks, the application and the technology of the sensor and all the software that is between that sensor technology and the application that eventually makes the smart sensor, all the tasks can be grouped in three camps. One is the actual communication protocol, so the part of the software that deals with the communication protocol, and mainly depicted by the functionality and described by the functionality of the OSI model of the data link layers, the network layer, and the transport layers. Then you have the system level set of tasks that deal with operating system type things or tasks, and also performance evaluation, storage, running the statistics of the system, and then the services. So services are those that enhance the application, but they have usability that transcend that specific application. So they are deployed as services from a modularity perspective, so they can be used in different applications. And some of them you can see there: localization, coverage, security, synchronization, data gathering, cross-layer optimization, and things like that. Those are the three main groups of the software tasks that you find in an application that is going to bind sensor technology and some wireless sensor network application. From an application perspective, the wireless sensor networks can be classified in two groups as they are being used today, but there are a lot more applications that I'm sure can be found. One is monitoring and one is tracking. So tracking refer to the ability to know where something is. So you can have a sensor that aids you with the tracking of some asset or some type of equipment. As a contrast with monitoring, or as a contrast with tracking, monitoring refers to actually gathering data and sending data about the environment of that which the sensor is attached to. So in a sense, monitoring is a little bit more comprehensive than just tracking the location of something. And here's a nice chart. When we look at the sensor networks and these two groups of applications, we can see tracking for each of the domains, some of which we have discussed already. In the military, so you can track enemy forces, so sort of like surveillance. For habitat, you can track different animals to learn about the movement, the behavior of a species, and study those. In public and industrial application domains, you can track traffic, and you can also track automobiles And then in business, you can track individuals. On the monitoring side, in military, you can have security detection. So now these are sensors that are collecting data as security is concerned, how many people, the flow of different, I guess you could say, enemy forces, and also your own forces to measure efficiency and things of that nature. On the habitat, you can monitor, not just track, like in here, not just track animals, but actually you can monitor specific things about certain animals or species. You can monitor the speed of a bird or things of that nature. That gives you an idea. On the public side, you can monitor buildings, you can monitor bridges, you can monitor machines in factory, you can monitor the state of inventory. If you can have smart shelves, where actually a sensor could be looking at the weight of the shelf and trying to track when the inventory has been deployed in a store, for example. You can certainly monitor chemical processes and chemical agents, as well as machine. So a big part of the Internet of Things and smart sensors is the ability to anticipate when machines are going to need calibration, they're going to need some type of maintenance. So that type of monitoring is very important. It's one of the areas that is seen as the most promising for this type of cyber physical system technology, because downtime of machines is very, very expensive. So if you can smartly deal with that instead of reacting to it, that could save a lot of money and really have a big impact on business. Then you can also have health type of monitoring, all kinds of monitoring for patients, and as well as weather type of monitoring for in the environmental domain. So you can see that there are a lot of opportunities for the whole thing of the Internet of Things, having RFID technology for identification, coupling that into wireless sensor networks that bring not only that identifying data, but other type of tracking and monitoring data, all the way to some type of database and analytic type infrastructure. So that's what we're talking about for this complex cyber physical system that uses the Internet of Things as a backbone. So that's the end of the chapter, and we'll end up here. Okay? Thanks.